For section 3.6, we're going to talk about inverse functions. And inverse functions are basically functions that have been flipped around the identity function. Now, that's the function where we basically draw a diagonal line across the quadrant going through the origin. It splits the quadrants sort of in half, and it basically is y is equal to x. So you remember that function. If you flip something around the identity function, and it has an inverse. And if it is actually a function, then it has an inverse. So we have a couple of equations or functions here given to us, and we're going to check to see if they are inverses of each other. Basically, the way we do that is we check the composition of these functions and see if they both come out to equal x. So in other words, I'll take f of x, and I'll say I want the composition of f with g. So I'll write the g of x function here. And I'm going to take that f of x function, which is 3 times x, that's where I'm going to insert the other function, plus 4, and see if it comes out, when I solve it, if it comes out to be just equal to x. Okay, so I have to put the g of x function in here. So I have 1/3 x minus 4/3. So a little bit of math, I'm just going to say, this is really equal to 3 times 1/3 x. Well, and that's just 1x, isn't it? And this is equal to 3 times negative 4/3, which is going to be the numerator and denominator here cross-reduced. So that's going to be minus 4. And then I'll bring down my plus 4. And what it is, of course, these two are going to cancel. And I'll have this one is equal to x. So far, so good. Let's check the other one. I'll say this is g of f of x. Or this is the g with x composition. And I just take the g of x function, which is 1/3, times, and here's where I'm going to insert the other function, minus 4/3. So I'll put the f of x function in here. It is 3x plus 4. And then I'll do some multiplication. I'm going to distribute this 1/3. I'll say 1/3 times 3. Well, that's just 1x, isn't it? And 1/3 times 4 is going to give me my positive 4/3. And then, of course, I bring down my negative 4/3. And these two will cancel, and I'll have this is equal to x. Both of these functions came out equal to x. Both of the compositions came equal to x. Therefore, I can say, yes, they are inverses of each other. Let's check the next one. First, I'm going to do the composition of f with g. And I'll take this f of x function, and wherever it has x, I'm going to insert the other one. So here's my g of x function, 1/2 x plus 7. I just have to distribute this 2. 2 times 1/2 is going to give me just 1x. 2 times 7 is going to give me 14. And then I come down and bring my 7 down. What I end up with here is x plus 21. So it did not come out equal to x. That's a problem for me. Let's just do the other side of it just for practice. So if I insert the f of x into the g function, I have 1/2 times the other function. There's where the x was, plus 7. And when I put the other function in, it's 2x plus 7. So now I just distribute 1/2. That gives me x. And this is going to give me 7/2, isn't it? Plus 7. Well, I want to add these halves together. So I'm going to change my 7 into something over 2. It would be 14/2 would be the same as 7. And then I can add them together. I'm just doing this so you'll have a little practice at it. 7 plus 14 is going to be 21. So that's 21/2. It's not even the same as the other. And these are no. They didn't both come out equal to x, so they are not inverses of each other. Let's do another one that's perhaps a little more complicated because it's got all these fractions in it. So the first one is going to be f of g of x. And I'll take the f of x function, and it's got an x in the numerator and an x in the denominator. This numerator is plus 5 here. And I'm going to have to go down here and say it has the x in the denominator. And that's going to be plus 3, isn't it? Okay, now let's put the g of x function into where we left these blanks. So this is going to be times 5 minus 3x over x minus 2, and I have to insert it in both places. All right, now I need to do some cleaning up of this function. And really, if I recognize that this has a fraction in it, and this has a fraction, and both of these fractions have the same denominator, I really want to get rid of it. So what if I multiplied this numerator and this denominator by the same thing, by this binomial that's already in the denominator? Now this is the same as having a 2 over 1, and this is the same as a 5 over 1. These are whole numbers, right? So what I'm going to see if I can do is just clean it up a little bit by getting rid of this first, okay? So first step, I'm going to take this as a first step. And there's several different ways, of course, you could do it. Now, this is just one term right here. Remember, this 2 is multiplied times this complex fraction. So I can just multiply it times this second term and leave off multiplying times that leading coefficient later. So I'm going to do that and come down here and say, I'm going to still have the 2 multiply, but when I multiply this one times my fraction here, I end up with just 5 minus 3x. I cross-reduced and got rid of that denominator. And then I say plus 5, and now I have to multiply it times, because this is a second term, isn't it? It's separated by addition. So I'll say that's 5 times x minus 2. Hopefully that makes sense to you. You could do it another way. You could go ahead and distribute the 2 in the numerator here, and you would have 10 minus 6x, and then do the multiplication. Either way is fine. So let's do the same thing down here. I'm going to take this x minus 2 and multiply it times my first term, which in effect eliminates the denominator. And then I'm going to multiply it times the second term. I'll just write it down so you can see what I'm doing. Okay, and then we start distributing this multiplication. So here I'm going to have 10 minus 6x plus 5x minus 10. Okay, that's my numerator. My denominator is 5 minus 3x plus 3x minus 6. All I did was distribute multiplication. Now let's simplify this numerator. I have a positive 10 and a negative 10, don't I? Positive 10, well, I can basically just get rid of those. And then what I have here is negative 6x plus 5x. Well, that ends up being negative x. That's my numerator. My denominator is going to have, this 3x is positive, this 3x is negative, so they're going to cancel each other out. What I have is 5 minus 6, or negative 1. I hope you can see that. And then, of course, negative x divided by negative 1 is just x. So this one did simplify down to just plain old x. You might want more room for the second part of it. Than I've given you to write with here. I'm going to see if I can get it on this page, but just go up as far as you can, because I didn't give you enough room probably. So I'm going to take g of f of x, and I'm going to substitute into the g of x function, which has this complicated numerator again. And that's where the x is, right? It's 3. Sorry, it has to have 3 there. 3 times that. And then in the denominator, I have the x value, and it's x minus 2, isn't it? So x minus 2. Now let's substitute the f of x function in there. So it's going to be 2x plus 5 over x plus 3 in both places. Okay, so now let's do some of the same thing. I have a denominator that I'd really just like to get rid of, right? So I think I can go ahead and do that. And for some of you that I didn't do the distribution before, let's just do it that way so you can see the second way you can do this. Simplifying this before I cancel out the denominator, I'm just going to distribute this negative 3 up here, okay, to both of these. So it would be 5. And I would say, then I have to say this is a minus or plus. I'll say plus, and in the numerator I'm going to have a negative 6x. And then I'm going to say, negative 6x. And then I'm going to say this is minus 15. right? So all I did is distribute this -3, and it changed both of these signs to negative, and I changed this to a positive so you could see that I've already distributed the negative. And that is over x plus 3. So if you want to put that in brackets, you can. And then what do we have next? Well, the denominator of it, we'll just leave it like it was. It was 2x plus 5 over x plus 3. So I'm doing it a little differently than I did before, just so you can see the options here, because some of you are going to be wondering why I didn't do the distribution here first before I did the simplification. So this is the way you would have done that if you wanted to do that. So I've got this big fraction, and I really want to take it and get rid of this x plus 3 denominator in both of them. So what do? I multiply times that denominator, x plus 3 over x plus 3, which is really just the number 1, right? Anything over itself is the number 1, so I can do that. And I've multiplied this fraction, and I will actually clear these denominators, but I still have to multiply x plus 3 times 5. So I'll do that first. X plus 3 times 5 is going to give me 5 times x plus 3. And then when I say x plus 3 times this fraction, I end up with negative 6x minus 15, because it just cleared the denominator. Let's say the same thing down here. X plus 3 times this fraction is going to clear the denominator. I'll have 2x plus 5. And then when I multiply it times a negative 2, I'm going to be careful to keep this in parentheses because I'll have trouble otherwise with my negatives. Okay, now let's do this. Let's say 5 times x is 5x. 5 times 3 is 15. We still have minus 6x minus 15. And down here we're going to say 2x plus 5, and then I'll say negative 2 times x, and negative 2 times 3 minus 6. All right, let's see what we can clear. I have a positive 15 and a negative 15 in the numerator, so those go away. And I have 5x minus 6x, or negative x. Down here, it looks like I have a negative 2x and a positive 2x. And I have 5 minus 6, which is negative 1. Once again, it looks like it's just x. So both of these actually solved to x. In other words, the composition functions came out to x for both of them. So are they inverses of each other? The answer would be yes, they are. Now, one thing we want to note at the top of this page is this statement: only one-to-one functions have inverses. So when you think about a function that's one-to-one, you know that it has no two different ordered pairs that have the same second component. And that's what we call a one-to-one function. Now, only those one-to-one functions will have inverses, but there are some functions that are actual functions, but they may not be one-to-one, such as a quadratic function. If you think about that, if you inverted it across the identity axis, if you're that identity function, it would no longer be a function. And that's really what this is talking about. Do they have inverse functions or not? So on this page, this next page, we're going to look at how to find the inverse of a function that is a one-to-one function. And the way we do it is we replace f of x with y in the equation, in the function, and then we interchange the x's and y's and we solve for y. So there's really 3 steps to it. And then we can prove that it is an inverse of the function by doing the compositions like we did on the previous page. So let's look at this one. This is a one-to-one function. It's already told us that. And then we're going to find the equation. We're going to say first, step 1, and I'll just write these the first time. Step 1, we're going to change f of x to say y. And then step 2, we're going to interchange all the x's and y's. So it'll be x is equal to 1/2 y minus 1. And step 3 is simply solve for y. So sometimes it's a little tricky. I like to get the y onto the left-hand side, so I'll just say this is 1/2 y is equal to x plus 1. I just traded sides with it. And then I'm going to have to multiply everything by 2 to get y. So this is y is equal to 2x plus 2. And now I'm going to go back to function notation. So the function of the inverse is f of -1 of x. That's the inverse of f of x. And that's equal to 2x plus 2. That's my new function. So how would I prove that they are inverses of each other? Well, I'm going to put the proof over here. I'm going to do the composition. I'm going to say f of that inverse of x. And this one is going to take the f of x function, and where it had an x in it, I'm going to insert my inverse function and see if it solves and it becomes x. So when I say 1/2 times 2x, I just get x. 1/2 times 2 is plus 1, and then this is minus 1, and of course that does come out equal to x, so that part checks. Let's do the other way. Let's say the f of -1, the inverse function of the f of x function we'll say with the f of x function, that particular one, and that one is going to be 2, and where I have an x, I'll insert the other function. That's the whole f of -1 function, the inverse function, and I have to insert 1/2 x minus 1. Now let's do the math. 2 times 1/2 is just x, 1x, and 2 times -1 is minus 2 now. And then I had a plus 2, which of course they canceled, and this just came out to be x2. So yes, I got the correct inverses, and that's my proof. So how would I draw these? Well, first, let's draw the identity function, because we know that an inverse is actually flipping. It's rotating around the identity function. You should always be able to do this function without looking at anything. It just splits both of these quadrants in half. I'm just going to see if I can line this up a little bit. And I'm going to draw a dotted line. Hopefully I got those right. And I'm going to label it y is equal to x. You can label it y is equal to x or f of x is equal to x. That's the identity function. So where was the first function? Where is 1/2 x minus 1? Well, 1/2 x minus 1, if I wanted to put in some points for it, I could. And that's what you should do. And you could easily go into your calculator and graph it. And maybe that's a good way for us to look at this. Let's get our graphing calculators and do that. So I've gone into my graphing calculator here, and I'm just looking at the y equal. And you'll note that I've already put down in the third one, I put y is equal to x. I put the identity function. I like it to be the one that's, my graphing calculator's color, so I like it to be the one that's black. Then I'm going to put the function, f of x function, right here. I'm going to say that is, I'll go ahead and put it in parentheses, 1 divided by 2 times x, and then I'll say it's minus 1. That's the first function. Now let's put the inverse function down here. It was 2 times x plus 2. And I've got my 3 functions. Let's see what they look like on the graph. So that's the first one. That's the blue one. That's the second one. And there is the identity function. So yep, they are inverses. Do you see how this flips across? It's just rotating itself. The blue one is the actual f of x function. It's rotating itself across the identity function, and so they should cross the identity function at the exact same place. The nice thing about inverses is that for every x value, you're going to have, every xy value, you're going to have the opposite values on the other function. In other words, let's find a couple of points and I can show you what I mean. So this is my x values. This is my f of x function, this is my inverse function, and that's the identity function. I really don't need the identity function, so it's just kind of out there on the side, which is why I like to put it in the third one, so it's out of the way. So if I want to look at how to graph the first function, f of x, I'm just going to find a couple of points. It has 0, -1 on it. So I can go to 0, -1, and I can draw a dot there. And then the next one, I kind of want to do some others. How about -2, -2? That's a good one, isn't it? It looks like that's where it's going to cross the identity function, as a matter of fact. And let's go even further negative than that. I'll go up here so I can go a little. I just want to try whole numbers. So let's do -4, -3. -4, -3. And you can see it did cross that identity function right there, didn't it? How about 1 over here? What if we tried 4 and we have 4? 1 is one of the points that we have. And at this point, I really can draw a line, can't I? Get some sort of straight edge here. And I can say this is my f of x function. I'll label it. This is f of x. Now, that's the first one. Now, I plotted those points. If I have a true inverse, then I can sort of reverse the points. This one was 4, 1. So the point 1, 4 should be on the inverse. 4, 1, opposite of that would be 1, 4. That point should be on the inverse. This point was 0, negative 1. Negative 1, 0 should have been on the inverse. Negative 1, 0 should be right here. This point, let's go down to here because this is really going to be the same point on both of them. But this point is negative 4, negative 3. So I should have a negative 3, negative 4 on the other line. You see what I'm saying? So I should have the opposites. If I change out the x and y values, let's just check what I just said and see if it's true. What's one point that's on the inverse that I wanted to check? Well, I wanted to check 1, 4, right? So I look at this one and I see where is x equal to 1? Here it is. On the inverse, which is this one that I graphed here, I have 1, 4. So that point really is on the inverse. Let's check another one. I said I should have, since I have 0, negative 1, I should have negative 1, 0. And I look here and I look to see if I have a negative 1, 0 is on the inverse. So I've got negative 1, 0. Okay, so that's good. And then I look to see if I had negative 3, negative 4. I want to go to negative 3 and see if the y-coordinate is negative 4. And it is. So I can basically say, I knew I had the inverse because I did the proof. So every point that I have on my function, I should have the reversal points on the inverse. In other words, all I have to do is switch out the y and x values, and this is my inverse function. So this is the inverse f of negative 1 of x. Now on page 35, we're going to do a graph. We're going to do the same thing, but this one is really looking at a cubic function is what it's looking at. I know because I can see this is really going to be a transposition of a transformation of the x cubed, isn't it? So I'm sort of expecting my graph to take a curvy shape somewhere in here because I know that's the shape of the cubic graph. But let's go ahead and find the inverse. The inverse is going to first say y is equal to x minus 2 cubed minus 1, and then I'll change out my x's and y's. And then I'm just going to solve for y. So first I have to get this y minus 2 cubed isolated. It's going to be x plus 1. I'm going to switch sides with this. Because I really want to put it over on the other side. And what I'm going to do is cube both. I'm going to take the cube root of this side. So I have to take the cube root of this side. I have to take the cube root of the other side. So why don't I switch them around and do that? This is going to be the cube root of y minus 2 is just y minus 2. And that's going to equal the cube root of x plus 1. So I just took the cube root of both sides. So now what do I do? Well, I really need to get rid of this negative 2, so I'll add 2 to both sides. And my final inverse equation is going to be the cube root of x plus 1, and then outside of the radical, I'm going to say plus 2. All right, so that's going to be my inverse. I'll write it in that function notation and say it's really the cube root of x plus 1 plus 2. All right, now here's the proof for it. It's not really that difficult to prove, and you can come over here and see if we got it right. All I have to do is take those compositions, the function f of negative 1, or f of the inverse, and I'm going to take the f of x function, which was going to be right here. It's got to have where x is. I'm going to have to say cubed minus 1. So what do I insert in this one? Well, I'm going to have to insert this function that I just got, right? So I'm going to say that is the cube root of x plus 1, and then I'm going to say plus 2. All right, so how do I do this? The math is not really as hard as it might look at first. When I figure this out, all I've really done, these parentheses aren't multiplying anything. And I can write it again to make it a little clearer for you. What it's really saying is the cube root of x plus 1 right here, and then it says plus 2 minus 2, and all of that has to be cubed minus 1, okay? The brackets that we put in to insert it are a little bit confusing, but when you write it like this, you realize this 2 minus 2 just gets canceled out. And I am taking a cube root and I'm cubing it, so I really get rid of the radical. This is x plus 1 now. And then I have x plus 1 minus 1, which is just x. So that one worked fine. Let's do the other one. The inverse of the f of x function. The inverse function of the composition, the f of -1 with the f of x, I guess you could say would be better. And I'm going to take this inverse function, and everywhere I have an x, I'm going to insert the other one. Now that does look a little confusing, so let's see if I can clarify it. So I had an x right here, didn't I? And it's under the radical. I'll just put this kind of bracket, and this plus 1 is also under the radical, and then I have to say plus 2 out here. So what is the function that I'm inserting there? I'm going to insert x minus 2 cubed. And then I have to put the minus 1, don't I? Now, once again, I've got this bracket, this parentheses that doesn't really matter. If you want to see it a little clearer, I really have x minus 2 cubed minus 1 plus 1. That's what's under the radical. And then I have plus 2 over here. So what's going to happen? Minus 1 plus 1 cancels. I'm going to take the cube root of something that's cubed. So all I have is I got rid of the radical and I got rid of the exponent, didn't I? And of course, x minus 2 plus 2 is just x. So they both check out. That's the proof. Now, how do we graph them? These are a little tricky to graph. You could plot points if you wanted to. You can also do it with your graphing calculator, which I'm going to show you real quick. I went in to my y equals, and I typed in the first function, the f of x function, up here. I said x minus 2 cubed minus 1, and then I typed in the inverse function, the cube root of x plus 1 plus 2 outside of the brackets, and then I typed in the identity function down here in the third one, just so I could see it. And then I'm going to go to graph and show what it does. Now, of course, I expected these curves because I'm working with cubic functions, so I expect that S shape to happen, and it looks like they are inverted. It looks like it's inverted. It's flipped around the identity function. So now all I need to do is find some points so that I can graph it. First, I'm going to come out and put my dotted line where my identity function is, because I want to prove that it flips around or it inverts itself around the identity function. So this is y is equal to x. The next thing I want to do is go to the table. So I go second graph and come up with this table of points. And I don't need the points that are like really huge and ungraphable, right? I just need some that I can graph, and I'm going to pick the ones on the first function first. I have a point that I can graph here. It's 0, -9, isn't it? And that's on my chart. So let's find 0, -9. And that looks like this point right here. And then let's go find another one. I've got 1, -2, don't I? 1, -2 would be right here. Now this is going to curve, so I'm probably going to want to find a few more points. And then I've got 2, -1. So there's another one that's kind of 2, -1. That's where it's actually making the turn, isn't it? And then I expect it to turn and go up because it's got to be that S shape. What happens next? I've got 3, 0, don't I? So it's crossing right here. And then I've got 4, 7. So I got 4, and I go up to 7, and quickly now I can see it's going to get off of my chart, isn't it? Let's see if I have another point that's actually on the graph. Everything else goes quickly off. 526, 623, but that's enough. I can pretty much draw a fairly accurate picture here, like this. Okay, and I'll just label it. This is my f of x function, isn't it? Now let's see if we can draw the inverse of it, and hopefully we'll draw it kind of accurately. Now, the thing I would do is take all of these points that I've got, and I would just reverse them. This point was 0, negative 9. I'm expecting negative 9, 0 to be on the other graph. This point was 1, negative 2. So I'm expecting, I said 1, negative 2. I'm expecting negative 2, 1 to be on my graph. This point was 2, negative 1. So what I would think would be on my graph would be the negative 1, 2, right? And this point, let's see, what else do I have? I actually had 3 zeros, so 0, 3 should be there. And then I had 4, 7, so 7, 4 should be on my next graph, right? Right about here. Okay, so how would that look if I graphed it? And you can check all of these points, right? Whoops, not drawing too great. You can check all of these points in your table and see if they are in fact on the graph of the inverse. So I would look for 0, 3, and it's there. I looked for negative 1, 2, it was there. I looked for negative 2, 1, it was there. What was another one? 7, 4, it was also on that graph. So you should be able to find all of those coordinates. But we know we've got a true inverse. Now that should have crossed those lines. I'm not really good at drawing them, but they should have crossed the identity function at the same point. So this is my f of negative 1, my inverse function. For the next example, we're going to look at a sort of a strange example because this one really starts with a quadratic function. Now, quadratic function is not necessarily a one-to-one function, but if we restrict it, then it is one-to-one and it is invertible that way. So they have restricted us to x's of greater than or equal to 0. So all we have to do to find the inverse for this one is change this to y. And then we're going to come up here and say, well, I'm changing out all of my x and y values. So I'm going to say x is equal to y squared minus 4. And I'm just going to make a note out here that all of these y's are going to be greater than or equal to 0. All the x's were greater than or equal to 0, so the y's are going to be that for the other. I've switched out everything. And then I say y squared is equal to x plus 4. And then I take the square root of both sides, and I say y is equal to the square root of x plus 4. So that is my inverse function, square root of x plus 4. I'm going to go through the process of proving it in case you were asked to prove it. So I'm going to take the f of negative 1, and I'm going to say that's going to take the f function, and everywhere I have an x, I'm going to insert the other function. And that other function is the square root of x plus 4. So when I take the square root of x plus 4 and square it, all I get is x plus 4. And then, of course, minus 4, and that one does come out to equal x. That part checked. So let's take the inverse and insert the f of x function. My inverse function, of course, was the square root. And inside that square root function, I'm going to insert the f of x function. And it's plus 4 under the radical. So what was the other function? It was x squared minus 4. Well, I can just simplify this down, can't I? If I get rid of those brackets, I've got x squared minus 4 plus 4. And all I've got here is the square root of x squared, which is x. So I've checked them, and now I'm going to graph them. Now, drawing my line, my identity function is the first step. I want that to be my dotted line on my graph. See if I can get it straight this time. And that's y equals x. And then I want to put in the other two. Now, I've plugged them in to my calculator because that seems to be the best way to do it. And when I plug them in, I have, for the first function, I have f of x, x squared minus 4. For the second function, I have the inverse, which turned out to be the square root of x plus 4. And for the third one, there's my identity function, just so I can see how they graph. I hit the graph button, and look what's happened. This thing is, of course, that's my first function. That's my f of x. And that is a parabola, isn't it? And remember, there's a restriction. It only is going to be applied where x's are greater than or equal to 0. So it's only going to use this part of the parabola. From where x is 0 all the way here. We can ignore that part right there. And so when we ignore that part, you can see that the inversion does match. Let's take a look and make sure, because we've already proved this with our proof, but let's take a look at the table. I'll go second graph and look at my table, and I'm going to plot a few points on this thing and just see how it comes out. So the first thing I see, and I want these to be reverses of each other, I'm going to plot some points on f of x first. I've got, first one I've got is maybe -2, 0 is one of the points I want to look at. But then I remember I can't have any x's on this function that are smaller than 0 because it was restricted to x is greater than or equal to 0. So let's start with x of 0 and find out what that is. It looks like it's 0, -4. So that's on my first one. This is on my f of x function, 0, -4. And then let's just do a couple more, okay? I'm going to look for something. Okay, how about 2, 0? That's where it's going to cross the x-axis. And then one more maybe will help me to do this. What about 3, 5? That's another point that I can look at really easy. So I know that I've only got, and I know that it could be equal to 0. I was okay with equal to 0, so this point is included on my graph. I can color it in, and I know I'm going to draw half of a parabola. So I know it looks like this. This is the f of x function. The half that I'm allowed to use, right? Because of this restriction, all x's had to be greater than or equal to 0. So let's see what the other one looks like. Well, if I had 0, -4, I should have -4, 0, right? If I had a 2, 0, I should have a 0, 2. And if I had, what is this one, 3, 5, I should have 5, 3. I've just reversed them all. And I've got half of a parabola here, which is really a square root function, isn't it? But you can see how they work. This is the inverse. The inverse function. You can see how they work, and they are matching and completely reversed around the identity function. And the points, if you want to check them, you can see the points in the graph do come out to be on the second function. My red one here has the same points. It has the 0, 2, and it has the 5, 3. I mean, the inverse points that I used do work, and that would be my graph. So with this page, keeping in mind what we've just done, we have not a function given to us. We just have the graph of the function, and they want us to draw the inverse. But they've given us 3 identified points on it. It's easy now for us to see what we do. Let's go ahead and put in the identity function just so you can see it happen. And I'll just draw that in with a dotted line. And I'm going to label it y is equal to x. And then I'm going to take these points that are on the first function, and I'm going to say, well, this is a -2, 0. So a point that should be on the other one is a 0, -2. There's the inverse of it. If I have this point, which is a -1, 4, I should on the other one have 4, -1. And this one looks like it's 0, 8. So I'm expecting 8, 0 to be on my other graph. Let's see if this looks like an actual inverse when we do it. And it does. This would be my graph of my inverse. So that's kind of simple to draw if I just have a few points identified on the other one, especially if it's a linear function, a straight line. That makes it really simple for us. Let's go down to the next part and see if we can take this function and find the inverse and then graph them in the same rectangular coordinate plane. And that's what we've been doing, and we'll go ahead the same steps that we've been. I'm going to say this is the graph that they want me to look at, or they want me to graph, is 4x minus 7. If I want to find the inverse, of course, I'll say, well, y is equal to 4x minus 7. And that means that x is equal to 4y minus 7. And then I need to get all this, I'll take 4y to this side and say that's equal to x plus 7. And then I'll divide everything by 4, and I'm going to just put it out front. Well, how about we do it like this? X plus 7 divided by 4. That'll do fine for what we want to do, okay? So this is going to be my inverse function. F of negative 1, x, inverse function notation, is going to be x plus 7 divided by 4. All right, here's my proof. Let's do the compositions. Let's say f of negative 1 of x, and that's going to equal 4 times, and we're going to have to insert the other function in right here, and remember there's still a negative 7 minus 7 there. What do I insert in here? X plus 7 over 4. And when I do that, I'm really just going to cross reduce. I end up with x plus 7 minus 7, which is of course just x. So that part checked. Let's do the other one. The inverse of the f of x function. And I'll take that one, and I'm going to end up putting it right up here, plus 7 divided by 4, and I'm going to insert 4x minus 7. Well, in my numerator, I've got 4x minus 7 plus 7, so I really just have 4x. And in the denominator, I have 4, so that just comes out to be x, and they've checked. So let's draw in the functions that we have. Identity function first with a dotted line. Let's see if I can do that. And that, of course, is y is equal to x. And then let's take our graphing calculator and go ahead and enter these two functions. And I haven't cleared these yet, so I'm going to go down and clear them. And then I'll go back to the first one, and I want to say 4 times x minus 7. And then for the second one, I'm going to put it as a fraction. So I'm going to put it in parentheses. I'm going to say I've got x plus 7. And I close this parentheses and say divided by 4. And check it and see if I've got them right. And of course, I've got the identity function in the third one there. And let's see what it looks like when I graph them. There's the first function, there's the second one, and there's the identity. And they look like they're crossing perfectly. So I can go and just find a few points on one of them, reverse those coordinates for the others. Let's see what the table tells me. Otherwise, I'll be plugging in points of my own. And I'm going to look for points, let's see, on the first one. I'm going to look for something it's easy for me to graph. Now, these negative 15, negative 11, here's one. 0, negative 7 is a good one, easy for me to graph, and it's on the first one. So I'm going to go 0, negative 7. And then I'll see if I can find something else. 1, negative 3 looks okay. 1, negative 3. And then I'm going to find, what about we just go a little further out? 4, 9. 4 and 9. I think I got those right. So I can draw a line straight through those. They should be in a straight line because these are linear functions. And I'll label that. This is f of x. Okay. Now, the points I had should be, the reverse of them should be on the inverse. So what did I have? I had 0, negative 7, right? So I should be able to find negative 7, 0. I'm just going to kind of come up and check. And I do. I have negative 7 on the red one. That's the inverse. I have negative 7, 0. So I've got negative 7, 0 is right here. And then another point that I had was 1, negative 3. So I should have negative 3, 1. And I do. Negative 3, 1 is right there. And the next one I found was, what was it? 4, 9. So I should have 9, 4. And there is 9, 4. There's 3 of the points that I need to graph it. It's easier to draw. You can draw it with 2 points, but really 3 makes it much easier to graph. And this is my inverse, f of negative 1. Sorry, f of negative 1 of x is the way I want to write it. And the last page that we have to cover is really fairly simple. Remember how there's a vertical line test to see if we have a graph that is truly a function. Well, to see if there is an inverse of a function, what we have is a horizontal line test. Because remember, we're going to be flipping it around the identity function. So it was going to, when it changes, we're not going to be, a vertical line won't tell us anything, but a horizontal line on the existing function, if it crosses it more than once with a horizontal line, then it does not have an inverse. But it might actually be a function, but it doesn't have an inverse when it doesn't have a, it is not a function when it is inverted, therefore it doesn't have an inverse function. Does that make sense? All right, so we're going to do a horizontal line test. This one, if I draw a horizontal line here, you can see I cross it multiple times because that is a horizontal line. So no, this one doesn't have an inverse function that is an inverse that is a function. Same thing happens here, and most parabolas are that way. Horizontal line crosses it more than once. It does not have a function that is an inverse, does it? Here's another one. I can invert it, but the function I get will not be an inverse. And this one is okay because I can draw a horizontal line anywhere on this and I'm not going to have a problem. It's only going to cross it one time. Now just keep in mind that most of the time when you have this parabola, you're going to have trouble getting an inverse with a parabola because they're not one-to-one functions. They have duplicates in them. But if you restrict it to just part of it, like the x greater than or equal to 0, then you can have an inverted function. That's just something to keep in mind.